Hello, everyone. My name is Jacopo Poli, and I'm the lead machine learning engineer at LightOn. Today, I'm happy to present Adam Gaier. I hope I pronounce it correctly. Senior AI research scientist at Autodesk Research. He's going to present his work on weight agnostic neural networks together with, it was developed together with David Ha. The work was done while he was at Google Brain and INRIA. And yeah, we will have a Q&A at the end. So at the end, you can either unmute yourself if you want to ask a question, or you can write it in the chat and I'll ask it for you. So I leave the show to Adam now.
All right, let me pull up my presentation quickly. All right. So thanks everybody for being here, or people who will be here later watching. So like I said, my name is Adam Gaier. This is work I did together with David Ha while I was at Google Brain, called weight agnostic neural networks. And so this work was originally inspired by animals like these baby iguanas here. So there's an underlying assumption in AI that complicated behaviors are the results of learning from experience. That we've got some general learning algorithms and we combine them with huge sets of data to train vast architectures that then are capable of learning nearly anything. But if you look at these newly hatched iguanas, this is their first experience with a snake. And if it had to rely just on learning and trial and error, it wouldn't get another experience with a snake. So something more is going on here, right? This iguana was born with some kind of innate behaviors, some abilities that it didn't need to acquire through careful observation and trial and error. And all animals are equipped with certain abilities like this from the moment of birth. Maybe less impressive, but infant mammals can nurse, baby ducks can swim, to say nothing for the vast array of insect behaviors. And just like animals, we're beginning to appreciate that machine intelligence also has some kind of innate abilities. So in a recent work called Deep Image Prior, it was shown that the structure of convolutional neural networks are so well suited to image processing tasks that even a randomly initialized CNN can perform tasks like super resolution or denoising, even inpainting, even if it's just trained on a single image. And there's been experiments with LSTMs in the early days that showed that for many of these time series problems, the parameter space of LSTMs was so rich in these kind of satisfactory solutions that many benchmark problems could be solved by just randomly guessing weight parameters. And there are echo-state networks whose architecture is composed of a reservoir of randomly connected recurrent neurons that are able to capture complex dynamics in time series and then replicate complicated input-output relationships in time. So this is a picture of one of my favorite examples of this concept, where they basically instantiated this pool of recurrent neurons into a bucket of water on top of an overhead projector. So these motors were kind of dipped into the water at rates translated from frequencies of somebody speaking. Then the wave patterns on the surface of the water were recorded by webcam, and then this 2D image uses input to a linear classifier. And this improvised setup alone was able to do some kind of simple speech recognition, able to classify between someone saying 1 or 0 with an accuracy of 95%. So all these architectures have what I would sort of think of as innate abilities. Maybe this bucket of water was not born with the ability to distinguish between the words 1 and 0, but the structure of the water lends itself to being able to effectively process time series dynamics. And we're going to use this kind of as a starting point for thinking about creating networks with innate abilities. So this is a quote from Jeffrey Ellman. He's a pioneer of recurrent neural networks in the 80s that sort of encapsulates our thinking here. So knowledge is not innate, but the overall structure of the network determines the kinds of information that can be received, and hence the kinds of problems that can be solved, and the kinds of representations that can be stored. So the structure of ComNets biases the network towards processing spatial patterns. The structure of recurrent networks and buckets of water have biases for patterns in time. And then you can have a representation like a convolutional neural network or an LSTM that sort of can't help but solve the problems they're suited to. We found it really interesting And we wondered if we could find the same kind of structures for reinforcement learning tasks too. And so just sort of fascinated by these innate abilities of animals and machines, this work asked the question, to what extent can neural network architectures alone encode solutions to tasks? And can we directly search for these innate architectures? So this is a different kind of neural architecture search. Rather than looking for networks which, once trained, perform really well, we're looking for networks that perform without any training at all. So networks with high expected kind of zero-shot performance that perform useful behaviors even with some random weights. So the main idea here is we want to search the space of architectures by de-emphasizing weights. This way we can judge the effect of an architecture on performance rather than the effect of the weights on performance. And so in this way, try to find architectures that are well suited to the tasks. So in kind of our ideal case, a way of estimating performance would be to initialize a network with random weights, test it, and repeat this process until we have kind of a good estimate of how it will perform just under random weights. But to do this, you need to sample a reasonable amount of the weight space. So this might be able to be done, in 2 or 3 dimensions, but because of the curse of dimensionality, even small networks, this quickly becomes infeasible. So sort of to get around this curse of dimensionality, we introduced a constraint into our networks. And that was that we would use a single shared weight value for all of the connections. So this reduces the number of weight parameters in a network to just 1. And so, when we collapse the dimensionality of the space to 1D, this is then, becomes pretty easy to sample. And so then the idea is that we can estimate performance based on several rollouts, with each rollout using a different shared weight value. And this can give us an efficient expected performance of an architecture. So networks that we find in this way, we're going to call weight agnostic neural networks, or WANs. So these are networks that can be expected to perform well with a single shared weight, and even when that weight is assigned randomly. So the search process for WANs follows the familiar form of evolutionary optimization. We start with an initial population of solutions. These are our network topologies, and then we evaluate them on the objective function. We rank all these networks then from best to worst and vary the best performing to create a new population and then repeat. So let me dive a little deeper into exactly how we approach this process to create WANs. So we borrowed heavily from the classic neuroevolution algorithm NEAT, which simultaneously optimizes both the weight topologies and, in special cases, the activation functions of neural networks. But by removing kind of the weight optimization components, we're then left with a simple way to do topology search in the space of small networks. So this allows us to vary networks in one of 3 ways. So starting with a minimal network, we can either insert a new hidden node with a random activation function. We can add a new connection between some existing nodes. And so we're just going to keep the networks feed forward for now to keep things simple. Or we could change the activation function of a node. And so we've allowed here just to have a variety of activation functions, from kind of more, run-of-the-mill ReLUs and sigmoids to also kind of stranger activation functions like Gaussians and sines. So we can use these more exotic functions to more compactly encode relationships like symmetry, repetition. And since we're not training these with backprop, we're not training them at all, we don't have to worry about their derivatives, so we can kind of use whatever functions we want. So we're going to start with a population of just sparsely connected minimal neural networks. So at this point, no hidden nodes, just some inputs connected to some outputs. The idea is to slowly build up to the necessary level of complexity, starting only with these sparsely connected networks, allowing us to produce only the connections that we absolutely need. And so when we evaluate our networks, the goal here is to get a good idea of the performance of these networks with a random shared weight. So the general idea is to test these networks over many rollouts, each time with a randomly selected weight and a randomly selected seed for the experiment. Then our estimate of the network's performance is simply the mean, reward that you gathered over all these rollouts. So it's a lot of variance here. That's, random weights, we've got random environments. So to get some more stable performance values efficiently, rather than just actually using a random weight for each rollout, we instead used a set of values to cover the range of possible weights. So weight values of 2, 1, 0.5, -2, -1, -0.5. That gets us increasing, decreasing, or maintaining the strength of the signal, and possibly inverting it. So these values were chosen because they seem to capture most of the variance in performance. Values higher than 2 seem to all produce kind of similar behaviors because we're sort of saturating the activation functions as at every step the signal gets increased. Values lower than 0.5 also seem to perform similarly. If you can imagine if all the weights were 0, for instance, that no signal is actually going to make it from input to output. So it doesn't really matter what the topology looks like. So once we evaluated our networks, we ranked them according to their performance and their complexity. And complexity in this case is just the number of connections that they have. And there are a few motivations for this. One is simply just kind of Occam's razor, that we prefer simpler models when possible. And the other is a little bit more practical, just that we're only in this algorithm adding structures, never taking them away. So without any pressure towards simplicity, our networks are just going to continue to grow and grow, adding structures as long as they don't hurt. And this leaves us with sort of messy networks with many useless or non-functioning components that also can be kind of difficult to evolve as stepping off points. So this evolutionary process allowed us to find networks that perform with this weight agnostic constraint. And it allowed us to find networks that were architectures that are kind of specially tuned to their tasks. So here are 2 examples of behaviors produced using a weight agnostic neural network. So the task here is to control the legs of this little robot to make it walk over some uneven terrain. So the inputs are the joint and body angles, and it has some LiDAR and foot sensors as well. So this is the same WAN, just using a different shared weight value. So these are different behaviors, but both work. Both are using this network on the right. This is the WAN. So the nodes here are colored by their activation functions, and the connections are in blue. Again, all these connections have a single common weight value. And so we were able to find networks like this one that give us pretty robust walking behaviors with a variety of different weight values. And this is the highest performing one, but we also found some more simpler, more compact ones that also performed well with a lot fewer connections that did quite well. And even if we did this, we really played around like relaxing this feed forward constraint, and we get even simpler networks. So here's one where that hip output is connected to the knee output. This gives us a nice walking behavior with 6 neurons and a single layer. For comparison, this is the type of kind of general purpose network that's typically found in the literature to solve these tasks. So you see this network on the left here, this sort of general purpose network has no particular biases for this task, just a bunch of nodes, a few thousand weights, and a whole bunch of learning. Compare that to the networks that we found, which don't really require much learning at all to actually work. So we can find WANs for tasks that are have a little less grounded inputs as well. So this is a car racing from pixels task. And shown here are the results with this WAN with 2 random weight values. So we're cheating here a little bit because rather than processing every pixel, we learned to drive based on a latent vector of a VAE trained on random frames. But this shows that WANs can handle even these kind of more abstract inputs, not just relying on inputs that have some kind of embodied geometric meaning. And again, we can, with these, we can also find even much simpler topologies that still manage good performance with random weight values. And critically, though these found architectures can operate without any training at all, when we do train the individual weights, we're still able to reach the same levels of performance as these general purpose architectures. So what we're seeing here is just the same WANs that I showed you before, but with varied and learned weight values. And so we're not locking these networks into kind of a single behavior, just limiting the range of behaviors they can express to those with high performance. And that also tends to include those with the highest performance. So these were pretty promising results for us for reinforcement learning. So we kind of just wondered how widely we could apply this approach. So more or less for fun, we just threw this up on the cluster and ran this on MNIST and wondering if we could get a weight agnostic classifier. So, I mean, this is a little bit more difficult because the encoding of relationships between inputs is really well suited for maybe these reinforcement learning tasks. They've got low dimensional inputs, we've got embodied agents and kind of reaction and interaction with the environment. It allows us to kind of find fuzzier controllers. Maybe they aren't perfect, but they're able to muddle through and get the job done. Classification, on the other hand, is a much less forgiving problem. It's a problem where the design of architecture has long been a focus. But in any case, we set our sights on MNIST, and we trained a network and pretended this was a reinforcement learning task. So we had like an OpenAI Gym MNIST environment where each rollout the network got 1,000 samples from a training set and trained against this. And so even though the network structure is far from interpretable, we can still make some observations. So what I've done here is sort of exploded out the WAN that was used to predict MNIST. And what we're looking at is the output node and how it's connected to the input. So this is not a fully connected neural network. And so you can sort of trace back the connections from each output and see the subnetwork, which is responsible for predicting each digit. And that's why I also showed here the pixels that were actually used for each prediction in yellow. And so you can see that some networks, like between 0 and 8, for instance, use very little of the input field, where something like 5 or 4 uses a lot. So here's the full network again, with the visual field colored by the number of classes that were actually used for each prediction. And so we see in blue, those are the pixels that basically no class ever used for prediction. That it was not connected to the network. And you can see that these things around the edges where there really is rarely any information, the network's never bothered to actually connect any of those things up. So this is kind of interesting. And when this network is given a random shared weight, it has an expected accuracy of about 82%. So, much higher than chance, not that great though. This value is really dragged down by the performance of some of these lower weight rollouts. So at the right, what we have here is a heat map of the test accuracy on this WAN for each digit in MNIST for each weight value. And an interesting thing is here is besides some digits being easier to identify than others, notably 0 and 1, but also 6 and 7, some digits are easier to identify at some weight values. So WANs at like 1.5 are better at 2 and 4, while WANs at -1 are better at 3. So if a WAN at a different weight value can be thought of as sort of a separate network, we could also create sort of a crude ensemble of these networks. And when we make a prediction, then we can use every weight value and just give each weight a single vote on the correct class. And when we create an ensemble like this, our accuracy jumps up to like 91.6%, which is equivalent to linear regression with thousands of trained parameters and coefficients. And here we're just using this one weight. And if instead we just take the best single weight value, what we got on the training set, we had an accuracy around 92%. So a bit better than linear regression. And again, with far fewer connections and only a single weight value. Of course, this is still, far below the state of the art. And we had to do a lot of work to get here in terms of evolution and actually building these networks. But still interesting that this can be done without any weight training at all. And even when the weights are trained, in this case, they don't actually reach the same level of performance as, for instance, a 2-layer CNN. But that really shouldn't be too surprising. We spent a couple days of compute trying to find this WAN. Humans have been refining architectures for MNIST for decades. So if we would have found something better, it would have been a little bit embarrassing for human beings, I think. But the point of this work in the end was never actually to find a high-performing classifier, right? It was to explore a different perspective on architectures and architecture search. So to search for architectures that contain some innate biases and priors, to search for these biases. So that network building blocks like CNNs and LSTMs encode such powerful priors that they can do useful work even without training, leads us to consider this property weight tolerance as maybe a really good heuristic for finding new architectures and components. Weight tolerance shows that architectures are kind of representing the right things, like such as the spatial or temporal correlations in images or time series. And the architectures of WANs limit the solutions which can be expressed. The WANs here are not universal approximators like general ANNs. And this is good, right? They only encode the structures and relationships that are important to the problem. Just like the LSTMs that are so rich in solutions that they can solve benchmarks by random guessing of weight values. We want to create architectures that limit the space of possible loose solutions around those that perform well in the task. Enough that just random guessing is still a viable strategy. And it's promising that we're not only able to find networks that work with any shared weight, but that once these networks are found, that we can release this weight constraint, do learning, and still get state-of-the-art results. And this shows that the restricted range of expression of these WANs still contains the highest performing solutions. And if it's the ability to encode relevant relationships that make our best machine learning architectures work as well as they do, maybe we should be doing this for RL too. The architectures we learned with WANs are fit to the problem, right? They work without learning, while also not preventing any further improvement with learning. And so, these kinds of ideas around innate abilities in machine learning, rather than just only pure learning, have been circulating more and more in the neuroscience community as well. So this is a quote from Tony Zadar from a recent piece in Nature. So the first lesson from neuroscience is that the animal behavior is innate and does not arise from learning. Animal brains are not the blank slates equipped with a general purpose learning algorithm ready to learn anything, as envisioned by some AI researchers. There is strong selection pressure for animals to restrict their learning to just what is needed for their survival. So in many cases, what is needed for survival is not optimal behaviors, but passive behaviors like our WANs. So for instance, crabs, they don't have huge visual cortexes or complicated vision systems. Their vision is pretty horrible, both in range and acuity. And so to recognize predators, they don't first look at 10 million images of animals and classify them separately by level of threat. They instead have evolved to align their eye stalk to the horizon, and if they see anything move in the top half of their eye, they run away. And maybe we don't want our systems to be that simple. I don't think it was kind of the level of innateness that Zador was referring to, but there is a middle ground, right? Innate neural systems that are wired to set the conditions for learning, to guide what's possible and what's easily achievable. Brains aren't, general purpose learning machines, but they aren't totally hardwired either. There has to be a blend of these innate and learned behaviors. And this is not really a radical thing that I'm saying here, right? The search for architecture search as a whole has always been about the blending of kind of innate and learned behaviors. But this focus has always been about how architectures can help learning, which misses the point about how powerful architectures alone can be. So the best architectures for learning also work without learning. CNNs, LSTMs, these kind of components improve performance more than any hyperparameter search or reshuffling of components ever could. So the search for innate architectures and components, I think, deserves at least as much attention as the search for more trainable arrangements of these components. And we hope that this work is sort of a first step in exploring that direction. Thanks.
Well, thank you, Adam, for the presentation. I found the crab example really brilliant. Claps on Zoom are a bit weird, but you can put a reaction clap if you like the talk. And and now we can maybe move to the Q&A part. So if anyone has a question, feel free to unmute yourself, or you can write it in the chat and I will ask it for you.
I will go first if no one is deciding himself. So first, thank you, Adam, for this very interesting talk. I think this is some really, really cool work. I was wondering if, you probably have thought of that and maybe you have something to share about this. This reminds me a lot actually of the lottery hypothesis, of finding pathways, that are actually kind of better suited. So do you know if have you investigated the connection? Have you any idea on this?
I think that there's oftentimes some very similar ideas that the lottery hypothesis is a little bit of also another way of sort of thinking about this in terms of finding the correct architecture, and that we really don't need quite as sparse of architectures, and that sort of through this combinatorial starting places that we sort of find what this sparse thing is, but it's sort of coming at it from sort of a different way. I think there was also the Supermasks paper that was also a similar thing that sort of showed you don't really need necessarily all of that weight information, but just sub-networks that actually kind of move up or move down. So I think it's all kind of circling around some similar ideas about how important just kind of these initial setups are, but sort of coming at it from two different angles. So we're sort of trying to look what happens if we can actually build these things up, and I think the lottery tickets oftentimes are looking more like how can we narrow this down, sort of a pruning approach.
Okay, yeah, thanks.
We have a question in the chat from Daniel Elliott. Any work on using your structure searching approach with an inaccurate model of an environment and then using the actual environment to fine tune? And how much faster could a biped task be solved with sort of pre-training architecture search?
Yeah, so I think that's a really interesting idea. It's sort of a meta learning thing that, I mean, originally I hadn't thought about doing this sort of in a world model first and then training it on the real thing, which I think is sort of what Daniel is talking about. A lot of this I had thought of in terms of thinking of for more of a meta learning thing where we would train this in simulation and then we put this on a real robot, and then it's very easy to sort of quickly learn this. But in the end, it's still kind of, it's just one step removed. It's the same principle. I think for meta learning, these kinds of things could be really useful, because essentially what we're doing is we're sort of designing our search space with these WANs to basically only have good solutions. And so when you actually want to do this on the real world, then maybe it finds this quite quickly. So in terms of the second question about how much faster you could do this bipedal task with this pre-trained architecture search. I don't remember the numbers. We were a little bit hesitant exactly about to put those numbers in the paper, because it's kind of a complicated issue, because I mean, the number of rollouts we had to do to actually get that architecture first was a bunch, you know? And so how to compute that into there. When we did these experiments, it was very fast compared to other things. I can't remember the exact numbers. And we could also, if we started, for instance, from a fixed weight value and just went from there, you know, it's sort of like, if you start from a fixed value, it already works. So to get state of the art really only took a couple iterations to get there, but I don't remember exactly the numbers.
Thanks for the answer. Other questions?
Well, I have. Thanks, Adam, for your presentation. It was great. I was wondering, you talked about when CNNs and RNNs are as encoding excellent priors for their respective tasks. Recently, of course, we've been a lot talking about transformers. Do you know if attention mechanism have the same kind of property? Are there like good priors, or are they just computationally efficient for training?
I mean, I'm not exact. I mean, the kind of this attention mechanism is itself very much a prior. Like the attention mechanism itself is not actually trained to sort of transformer blocks. And it does seem like now, I mean, I gave this, you know, published this paper a year ago. It seems like since then transformers have really shown to just beat everything right now, which is like, you know, seems like in many cases they're doing better than CNNs and better than LSTMs, you know, and on all of these tasks, which, you know, it could be that they are, you know, that there is some inductive bias there. I kind of have a feeling that it's a little bit something else in terms of sort of this more like this bitter lesson in hardware lottery sort of thing, where I think transformers maybe are just able to blow past these priors just by having a lot more kind of compute and a lot more that we can do with them. And so I would kind of think that this is more as almost a meta thing, and that the space, sort of like how CNNs you know, seem to perform so well because we have GPUs, you know, that maybe that transformers perform so well because of the current hardware that we have now. And so this is also something that you know, I'm sure this is probably close to everybody here's mind about how hardware actually affects what kind of algorithms you can use and what things become successful, you know, that I think whatever is going on here, you know, like has to, you know, it's not just the hardware there, but the hardware opens up doors to what, you know, algorithms might be best, you know, in terms of what actually operates on this hardware.
Yeah, it's linked to the hardware lottery paper that
yeah, exactly.
Thanks a lot.
Thanks. Other questions? Otherwise, I have one.
Well, I actually have one more technical one.
Go ahead.
On the specific paper. I'm not sure I understood why you had to frame the MNIST classification as a reinforcement learning problem.
I'm not sure that we necessarily had to. I mean, in terms of there being like basically just so it would fit into the thing, just like a reinforcement learning problem, in that we did several rollouts with different weights. We could have done this with all the data, with everything, I suppose. Just to, there's a lot of evolution and a big population size, and so it's easier just to sort of have just to fit it into our framework that was already there. Like I said, it was more
mostly practical reasons.
It was mostly for practical reasons. I think if you did this, otherwise there are more things we could do. To be perfectly honest, I think I threw this up on the computer like 2 days before I left for my internship, just as a lark to see what would happen. And so it was more about what can I do in 2 days to test this on MNIST to see if it works.
Okay, thanks.
Thanks. In the meantime, we had a question in the chat from Felix. Is there some kind of upper bound of complexity you tested for? You said for the race car example, you cheated a little by adding a VIE to the mix. What are the limits without using these support architectures?
Yeah, I mean, I think that is something that there's I think the limit on this is actually pretty low for this particular approach. The way that we're doing it right now, we're adding one neuron at a time to add to this. So I think this is maybe a starting point. I mean, even with this MNIST example, this is actually a scaled down MNIST. This is 16 by 16 rather than 28 by 28, just because I didn't really think that we could even deal with that kind of dimensionality. So this is something that, because we're only adding one neuron at a time, and we only have, we can only take one pixel or one input at a time. I think it's, as it is, it's fairly limited. We could think of doing other things with this, for instance, like having, rather than, evolving kernels for convolutions, for instance, that took these, as smaller operations or something like this, or projections or something like this, some other way of compressing data. And maybe this could be a block in the middle that, that does some processing. But in terms of this just by itself, we're essentially using kind of just to prove a point, and we're adapting sort of an architecture search method that was developed, I don't know, 20 years ago, when people didn't even think that, that they could really do this kind of stuff. So in terms of the upper bound of complexity, I think there certainly has to be some, as it is now, you certainly have to throw something new with this to actually make this scale to, larger image sets or something like this, certainly.
Thank you. Other questions?
Hi, I may have a very naive question because I don't really understand everything. But is it possible to adapt this kind of method to, for instance, a tree algorithm or other kind of, like, for instance, in a random forest, you can choose which forest is best suitable in that way? I don't know if that's clear what I'm saying.
I'm not exactly sure what you mean, but I think in terms of, I mean, the idea that kind of, I think the core idea of this is that we have to, if you want, you could do an architecture search in a way where you try to de-emphasize training. So if you're talking about random forests, and I don't know if this would really work, if you can do random forests with different, numbers of trees or whatever like this, different kinds of splits, without actually training what this is, and seeing which turns out best, this would be more closer to that spirit. I'm not sure if that would really work. But the general idea is that so many of these things that we develop work well, that actually work well with training, work well without training. And so there's this problem in neural architecture search where we really get trapped in this like loop of learning to learn, where you create an architecture and then you have to train it to completion on the test set to see how well it did. That maybe we can do this just by doing this without any training at all, and that would be maybe we can judge things by that.
Okay, thanks a lot.
I have one more question, perhaps more naive than Ruben's. So, of course, you showed that these kind of architectures perform really well without training, but they cannot reach the level of performance of general architectures if we take training into account. So do you think that this is an innate behavior, a limitation, a necessary trade-off, or do you think that there might be a way to overcome this and become better at learning?
Okay, well, let me first clarify. With the MNIST, we did not reach that. With the RL things, we got basically the same level of state of the art once we actually did do training. But your point is well taken. I think no matter what we're doing here is, if you compare a universal function approximator to this sort of what we're building here with these WANs, which are not universal function approximators, there's a limit in what functions they can produce. Maybe in these cases we were able to still get the same best results, but you know, from a theoretical standpoint, of course, we probably can't reach every nook and cranny of the search space that a universal approximator could. I'm just wondering how much that matters. And if we have, for intelligence, if we necessarily need to have the actual perfect optimal, or if we need to be, you know, just good enough, or if we can get, I mean, so far it was pretty encouraging that in these RL tasks, when we did find something that without any training was quite good, we were able to then go from there to the optimum. I'm not saying that's always going to happen, but I think that we're always sort of putting a cone around where we can look, that if this cone is around all those very, you know, optimal solutions, that it's quite possible, you know, likely that global optima is going to be in there too.
Thanks. Thank you.
Yeah, two more questions. So first of all, Felix was thanking you for the reply before, and also asking if there is a public source code. I think there is.
Yeah, there is. It's if you just search. I can also send it to you guys later to put up there. But if you search weight agnostic neural networks, I think it's there, and it's on Papers with Code as well. I believe. I think they link to it. So it's all up there.
And Daniel has another question. In your Ensemble results, what did your Ensemble look like the size of Ensemble, how the outputs were combined, and was this combination, like the coefficients, trained?
So all we did with the Ensemble is we took that one single network. And so this single network has just this one weight value that we can think of, just sort of like the gain or whatever. And we just, you know, technical, basically just did like a lin space, you know, of like 2 to -2, you know, at 0.1 increments, and just ran the network through with that level of weight value. And so this gives us basically just a bunch of different results, one for each weight. So, you know, you get one classification result with, you know, one. So if at 0.1, then it says this number is a 1. At, you know, at 0.5, that network then says it's a 5 or whatever. And basically for each one of these weight values, we just then said that's one vote, and whatever has the highest vote, that's what we said the digit was.
Okay.
So there was no training or anything like that.
Thanks. Sorry, my unmute button is a bit spotty. Other question?
I have a very practical question. Well, there are architectures that your algorithm finds don't look well suited at all for a GPU. So did you actually run that on GPU or just CPU?
Just on CPU.
Okay.
So even these networks that we ran, they were not even really well suited for backpropagation. So we then use like a population-based reinforce, or CMAS, or something like this. We use an evolutionary approach. So that is another thing that, you know, if you have these kinds of, I mean, we could have done this again, probably with some different activation functions that were differentiable, and maybe done this fine. But we found that we got better results actually just by using one of these more population-based things. Because I think, yeah, I think the derivatives were kind of messy because it's a bunch of different weird activation functions included. So I know you guys have been doing some work on some nice non-backprop ways of training networks. So this would also be something that would be interesting to see if that can work even better.
Thank you.
Yeah, other questions? Well, okay, I'm gonna ask mine then. One of the reasons we invited you actually was because I wanted to talk to you at the last New Rips, but like your poster was literally stormed by people, so it was impossible. And so I wondered, like, from these many discussions, for sure, some work has to like come out like inspired by yours, and it's a very open-ended question. Like, have you seen any work inspired by these weight agnostic neural networks that has done something that you think is interesting on top of what you did? Or in absence of it, what do you think would be interesting to do to take this idea forward?
I mean, I've seen a lot of people have referenced this in terms of some inspiration, some ideas, which is a little bit what the point of the paper was. I mean, I think David liked to joke that we had the record for the worst score on MNIST at a NeurIPS publication. So the point of this was not really necessarily as an engineering feat, but to get people to think about sort of architectures in a different way, about maybe hardware even in a different way. And I've seen lots of people referencing these kinds of things and with randomness. And I think there is certainly some nice work that could be done with this approach, with, again, sort of a more rich representation space. Like what we're doing here is very much just kind of piecing together some nodes and trying to solve some RL task. If we had the kind of representation that we could search to actually, rediscover convolutions and things like this, like then it would be interesting to see what else an algorithm like this could discover. I know, I don't know if you've seen work by like Kwok Lee that has been doing some kind of some other evolutionary approaches and being able to kind of rediscover things like backprop and dropout and stuff like this by learning these things. I think it would be, this is happening with with training algorithms. I think people should be really thinking about good ways that we can generalize maybe architectures in a way that we could, what is a form that that we could find both a convolution and and an attention block at the same time, because then this is something that really, in terms of this kind of loop of AI generating AI stuff, is something that's really like we need this for.
Great, thanks. Any other questions? Silence, so I assume no. I think we can close it here. I want to thank you again, and also thank Victoire that took the initiative to organize and then couldn't take it to the end. But yay. So everyone, if you want to add a clap reaction or unmute yourself and clap, and do how we do it in real world. Thanks again, Adam.
Thank you. It's really been fun.
And yeah, very happy to have listened to your talk, and see you soon.
Yeah, see you around. Next time we can see people. I'll see you.
Yeah, you're welcome to visit in Paris. Whenever COVID permits.
Yeah, looking forward to it.